We'll start the today's session. Today we'll discuss about a relative acceleration method in by adopting analytical approach. Now we'll start with a simple example so that we'll be able to understand it quite clearly. So here you have a mechanism in which you are asked to find out what is the acceleration of the ram and the angular acceleration of the connecting dot. The given mechanism is a single slider crank chain. So here we have the crank and then the connecting rod, and this is the ram is acting as a piston. So you are asked to find out what is the acceleration of this ram and the angular acceleration of the connecting rod. So if you're given such a problem, what you have to do is first you have to construct the kinematic diagram based on this particular mechanism. So here we can see the kinematic diagram which is being drawn. So in this case, this configuration is given as per the particular crank position, which is given as 40 degree with respect to the horizontal, and it is having an input condition of omega 2, which is given there, and the various link length is also being specified. You are asked to find out what is the acceleration of the piston, that is point C, as well as angular acceleration of the link BC, that is the connecting rod. Now, after doing the drawing the kinematic diagram, the next is to use the position analysis method and identify the unknown parameters for this particular configuration. So here the unknown parameter which is present is beta, which is the angular position of the, which indicates the angular position of the connecting rod with the horizon. So for doing the position analysis, you can just consider this particular larger triangle ABC. You can segregate it into two parts, so that is two smaller triangles. That you can do it by means of considering a perpendicular from B onto the side AC, right? So I've just directed a perpendicular from B onto AC. So I can name that particular point as D just for identification, so that I can mark it as D. Okay. Now I have two similar triangles. One is both are right angle triangles. I can indicate one as ABD and another one is CBD. Okay. Now using this condition, what we have to do is we can just correlate both these triangles by means of the edge BD, because BD is a common side for both the triangles, so that it will be much more helpful for identifying this beta. So what is to be done is you can take BD as equal to, from the triangle ABD, you can take BD as equal to AB sine 40, AB sine 40. So AB is known and sine 40 is known. So definitely you can find out what is BD. Now you relate BD with the other triangle, that is CBD, so that you can have it as BC sine beta. So already BD has been found out, so you can find out what is beta from that. Now corresponding to beta, you'll be getting a value of 13.9. So that is all about position analysis. The only unknown parameter that has been identified is beta here. You don't need this corner angle B, because if it is required, you can do that also. And for that, you have to consider the side AC also. Side AC will be AB cos 40 degree, and this will be BC cos beta. So that you will be getting AC, right? Some of those two will be AC. And you can apply the case of a condition of cosine law, so that you can identify what is the corner angle B. But for our analysis, that is not required at present, so we'll just stick on to beta and finish of the analysis. Now we have to go for the velocity polygon. In analytical method, there's no need for you to construct the velocity polygon by means of graphical method. What you have as per scale, you don't need to draw the polygon as per scale. Only thing is that you need to show the polygon by means of freehand sketch, so that you can identify the corner angles based on the configuration diagram. Okay. Now, as you know, this link 2 is the input link. Since omega 2 is given, so you can identify the velocity of any point on link 2. Okay. Now, B is a point on link 2, so you can identify what is the velocity of point B. And the direction of the velocity will be perpendicular to AB. And I'll show that. So this is the direction of velocity of B. So this is the direction of velocity of B. So that is perpendicular to AB. Okay, so I can mark that as VB. Okay, so that is VB. Now, and also you can identify what is the orientation for, or the direction of the line of action of point C. That is velocity of point C with respect to B. So we can draw that one also, because we require these. So if I draw it, I'll be getting it like this. Okay. So this is the line of action of velocity of C with respect to B. This is velocity of C with respect to B. Okay. Now, as you know, the velocity of C with respect to the fixed link will be always horizontal, because the fixed link is actually a flat surface, horizontal flat surface. And definitely the velocity of C with respect to the horizontal surface or the fixed link will be actually horizontal itself, right? So I can draw the line of action for that one also. That will be in this direction, right? So that I can call it as VC, because that is being considered with respect to the fixed link. So I can just call it as VC, right? So we have got all the line of actions of VCP and VC. So just you can identify the velocity polygon. I'll draw it on the left side. So first I'll draw the vector representing VB. So that has to be parallel to the vector shown at point B. So this is VB, right? And correspondingly, I can draw what is VC, because I already have the line of action for that one. Right? This is the line of action of VC. And I have the other line of action of VCB, that is the velocity of C with respect to B, that I have to draw from point B. So I'll just name it first. So this is point B, or I can call it as small b, because that is the velocity polygon. This is point A, that is a fixed point. Now from B, I have to draw the line of action of C with respect to B. So that has to be drawn like this. So that the intersection, I got it as point C. The intersection of the horizontal vector and the inclined vector, I call it as point C. Okay. So that I can name the vectors now. This vector, I will indicate it as velocity of B, and this vector, I'll name it as velocity of C with respect to B, and this one, the horizontal one, I can call it as VC, that is velocity of C. So this is how the velocity polygon appears. Now you need to identify the only known parameter for this polygon is VB. The rest of them you have to identify. So if you want to identify the velocities of C as well as relative velocity of C with respect to B, you need to identify the corner angles of this polygon. Okay. So to identify the corner angles, you go back to this configuration diagram. Now in the configuration diagram, you can see the link AB is being inclined at 40 degree. So the vector perpendicular to the link AB will be always inclined to the vertical by the same angle. That's what you have to understand. That means the angle between the perpendicular BD and this vector VB will be always equal to the 40 degree. Why? Because if I consider a line AB inclined to the horizontal at 40 degree, and if I consider a perpendicular to that line AB and find out what is the inclination of that line with respect to the vertical, you'll be getting the same inclination that you have obtained from the for the horizontal. That is a horizontal inclination for that particular line. Now that means if AB is inclined at an angle theta with the horizontal, then the perpendicular to AB will be inclined at the same angle with respect to the vertical. So that's what you have to understand. So this is how you identify the corner angles. So that means if I consider the polygon here, this polygon, if I draw the line, vertical line at point A, right? If I consider this vertical line at point A and then consider what is the angle between the vertical and the vector VB, that angle will be the same as that of the inclination of the link AB itself. So that means it will be 40 degree. So that means the included angle at point A, that means the corner angle at point A for this triangular polygon will be actually equal to 50 degree. So that means this inclination inside this angle, inside corner A will be equal to 50 degrees. Be 50 degrees, right? Now, if I want to identify what is the inclination of, similarly, you can adopt the same approach at point C also. Now, the link BC is inclined at an angle beta. So that means if you draw a perpendicular to BC, and if I consider the angle for the perpendicular with respect to the horizontal, with respect to the vertical, then it will be giving the same angle. That means if I consider the vertical at point C, then the angle between the vertical and the perpendicular to BC will be the same as that of beta. So that means if I consider the inclination here, the vertical here at point B, that means the angle between the vertical and VCB will be obtained as beta itself. That means that is angle 13.9. Okay. Now again you can see this VB is inclined to the horizontal at an angle of 50 degree, because the angle it has with the horizontal VC is actually 50 degrees. So that means this particular angle at point B is known. That means the horizontal at point B and vector VCB will be making an angle of 50 degree. So you can find out what is the inclination of the vector VB with respect to the vertical. So that is actually 40 degree. So 40 plus 13.9 will give you what is the inclination, what is a corner angle at point B. Okay, so this is how you identify the corner angles. And similarly, if you know what is the corner angles for the triangle at point A and B, then at point C you can identify what is the corner angle based on the law of triangles, where the total sum of the angle will be equal to 180 degrees. So that means corner C will be having an angle equal to 180 minus 50 minus this what we call it as 40 plus 13.9. So that means it is 53.9. So that means this angle inside this corner C will be known to us. Now, once the corner angles are known and one VB is also given, then definitely you can use the sign rule in order to identify what are the vectors VCB and VC. Okay. Now this is how you identify the vectors, magnitude of the vectors in the velocity polygon. Similarly, you can go for the acceleration polygon as well. Now in the acceleration polygon, what you will be trying to find out is, now for link 1, that is, sorry, link 2, that is the input link, only given parameter is omega 2. That means it doesn't have any angular acceleration, that is alpha 2 is 0. Now if alpha 2 is 0, that means the tangential acceleration at point B is 0. So not, because tangential acceleration will be equal to alpha into the radius of rotation. So that's what tangential acceleration is. Now the other type of acceleration which is present in this link AB is the centripetal acceleration, and that is directed towards the center of rotation, and we call it as the normal acceleration. Okay. Now the normal acceleration of AB, again we have to start with one of the points that is a fixed point. So I just named the point here. I can call it as A again, small a. Now what you do, you can find out what is the normal acceleration, that is the centripetal acceleration for AB, for point B, that is direct towards the A. Now if I do that, that will be obtained as R omega squared, is it not? So R omega squared means AB into omega squared, where R is the radius of rotation of point B. Okay. Now you have to draw the vector along the link AB, and that too directed towards the point A. Okay, because that is centripetal acceleration. So I can draw that vector now. This is actually a freehand plotting, just to identify the corner angles. So just I do that, which is parallel to AB. So this is what the vector is. Now this vector is actually inclined to the horizontal at 40 degree, because AB itself is inclined at 40 degrees. So you know that angle now. Now the next point, so we have already identified where the point B is lying, because that is the absolute acceleration of point B, because we don't have the tangential acceleration. So you got point B now. Now you need to identify what is the acceleration of point C with respect to the point B. Okay. So what I'm doing is, we have first the the centripetal acceleration of point C with respect to B, as well as the tangential acceleration of point C with respect to B. So both these components will be present, because link 3 will be having both alpha as well as omega. So let's consider what is you can already find out what is omega from the velocity polygon. So you take this VZB here. VCB is present here. You measure this quantity. Sorry, we have already identified by analytical method what is VCB. So since we have VCB, you can consider it as the centripetal acceleration will be equal to V squared by R, and R is equal to BC here, right? So based on that magnitude, we'll be identifying that. Okay. Now centripetal acceleration is known. So what you can do is, we can draw the plot corresponding to centripetal acceleration, and that will be directed along the link BC and from C to B. So I can draw that vector like this. So that is actually parallel to BC. That is parallel to BC like this. Now again we have another vector which is perpendicular to this already drawn vector now, and that will be the tangential acceleration. So I can draw the tangential vector representing the tangential acceleration as well. So that will be drawn like this, which is perpendicular to it. So I have drawn it. Okay. Now again, this point C is moving in the horizontal direction, because that is moving along a horizontal plane. So again, we can find out what is the absolute acceleration of point C. So that vector will be actually horizontal itself. So I can draw that vector again horizontally, right? So this is the vector representing the velocity of C. Okay, sorry, not the velocity, but the acceleration of C. So I got the point C now. Okay, name that intersection of the two vectors as point C. Okay. Actually, this point, the point in between B and C is actually C dash. So, so B C dash represents the centripetal acceleration of C with respect to B, and C dash C represents the tangential acceleration of C with respect to B, and the vector from A to C represents the absolute acceleration of C. So I can name all these. So I'll do that now. So this is actually acceleration of B, absolute acceleration of B, and this is acceleration, centripetal acceleration. So I can write this as C A, centripetal acceleration of C with respect to B. This is only possible means by which I can do that, because uh, we cannot have any subscripts or anything like that in this particular software. Yeah, I got one. So that is evident here. Just saw it. I can put this as a subscript now. Okay, that's fine. Okay, so that's how you do it. Yeah, so that is a centripetal acceleration of C with respect to B, and here I can call it as the tangential acceleration. The tangential acceleration uh, tangential acceleration of uh, C with respect to B. Okay, so that's what is being stated there, right? And this one from A to C, it is actually the acceleration of C, absolute acceleration of C, right? So this is how it needs to be understood. So here, what we need is we have just drawn this by freehand diagram, freehand sketch by. So these are not the absolute measurements. Just for identification of the various corner angles only, we have done that. So we need to identify what are the corner angles for analytical by to solve it by analytical method. So what you do is for AB, you know what is the inclination of AB, that is evident here, that is 40 degree itself. So that means the corner angle A, that is at this position I can indicate it as 40 degree. Uh, that is 40 degrees. Okay. So that is 40 degree at that point, corner A. And now the angle between the vector AB and the centripetal acceleration of C with respect to B, that is the between the vector AB, that is small AB, and BC dash. The corner angle at that point will be, we can calculate it as with respect to the perpendicular, it will be 50 degree. With respect to the perpendicular, it will be 50 degree. At point B, I can draw a perpendicular like this, a vertical like this, so that with respect to that point, with respect to that particular line, I can have a angle of 50 degree, right? So this angle towards right of B will be 50 degree, and the angle at the other position will be equal to 90 minus 13.9, because we already got it as the inclination of BC as 13.9. That means it will be 90 minus 13.9, or you can take it as 180 minus counter angle will be equal to 180 minus 13.9 minus 40 degrees. So that you'll be getting what is the counter angle B. Okay. So I can mark this position as if I indicate the angle B as so angle B angle B will be equal to 180 minus 13.9 minus 40 degrees. So that will give you what is the total angle at point B. Okay. Similarly, you can find out what is the angle at this position. That is the with respect to the vertical. With respect to the vertical, that means the vector AZB, the vector C dash C, the vector C dash C will be making an angle with AC. So that angle needs to be identified. Now that angle will be equal to now the vertical with respect to the vertical. This right angle will be equal to 13.9. So and this will be equal to 90 plus 13.9. Sorry, because if I draw a perpendicular here, you can very well identify it by yourself. Just it takes a little bit of time. That's all. So to closely analyze it and try to find out what is the angle. So the angle between the vertical and the vector perpendicular to BC will give you what is beta itself. So this is actually 90 degrees. So 90 plus 13.9 will give you what is this counter angle at C. Similarly, you can find out what is the angle at this particular position. So again, it will be having 13.9 here, and here you have again 13.9. So that means it is 90 minus. It will be 90 itself because it is perpendicular. So there is no need for identifying what is the angle at point C dash because that is 90 degrees itself. Okay, so that means if I take off this one and show it here, I can mark this particular angle as equal to 90 plus 13.9. That is 103.9, 103.9, right? 0.9 degrees. Okay, 103.9 degrees, and at point C dash it will be 90 degrees. So this is how you identify the counter angles. Now, what you have to do is you have to identify AB is known to us. AB is known to us because you know what is the velocity of you have already given omega 2, so you can AB. This AB represents R omega squared, and this BC dash also that is obtained also because we have from the velocity polygon. You know what is VCB. So VCB squared by BC will give you what is this BC dash. So these two vectors is known to us. So what you can do is you just consider uh, uh, you can just consider a vector connecting C dash and A, so that you can convert this into a triangle. These particular polygon into two triangles. That is, you consider a vector from C dash to A, so that will give you a triangle equal to A B C dash, and another triangle will be A C dash C. So this is how you try to identify. Okay, now you can identify the vector, identify the line AC dash based on the magnitudes and the counter angle at B, so that you'll be able to identify what is AC dash. So once AC dash is identified, now this counter angle is known, the counter angle at C is known, so that you can identify by using the sign rule again, you can identify what are the other vectors as well. Okay. So this is how you try to identify the various vectors. So this is how the analytical method has to be followed. So that is what is being shown in the remaining slides here. Now we have determined what is the velocity of B and C by just considering the various angles. So that is being done here. Now if we go for the acceleration polygon, after identifying what is, by applying the sine rule, we have identified that. So that is evident from these various equations they have used. So this is how they have identified that. Okay. Now, now the acceleration needs to be identified. For that, you just go for the acceleration, normal acceleration for B with respect to the fixed point A. So for that, you just take the velocity, or since omega 2 is given, you can take it as r omega squared itself, or else you have VB, so that VB squared by RAB also gives you the same result. So that is obtained as 40-degree inclined with respect to horizontal, and the tangential component is 0. That is evident here. Now the normal component for C with respect to B, you can identify by from the velocity polygons. You will be getting this quantity, and BC is known to us. The RBC is known to us, so that you can identify that quantity as well. Now that you obtained as 13.9 because that is acting along the link. Okay. Now, if you consider the other components can also be identified based on this geometry. So that's what I have shown in the acceleration polygon. So you just go through these literature and understand how it is being done quite easily, and then try to identify the various parameters. Okay. Now, after this, what we need to do is we have to consider the case of another acceleration that is known as a Coriolis acceleration. And this type of acceleration is present whenever a body is having a rotary motion with respect to another body. And that means that the body will be having both the rotary as well as sliding motion. It is not just having one single type of motion. It will be having a combined motion of sliding and rotation. So in that case, we have to consider the acceleration known as the Coriolis acceleration. Now, here we have a simple example for that one. So that is evident here. So here we have link 1 which is fixed, link 2 is a crank, and link 3 is a slider here, and link 4 is another link on which the slider is being moving. Okay. So here that means the point on the slider, will be having both rotary motion as well as a sliding motion. That means since the crank, the point B can be considered as lying on link 2 as well as it is lying on link 3 as well as it is lying on link 4. So that means point B is actually a coinciding point for all the 3 links. So what we can just imagine is that this particular slider will be having a rotary motion as well as a sliding motion, because the link 4 is also having a rotary motion, link 2 is also having a rotary motion, right? Whereas the slider is having a linear motion as such. And at the same time, if you analyze it at a combined motion, the slider will be having a rotary motion since link 4 is rotating, and it is having a sliding motion through the link 4. Okay. So if such cases are present, then we have to consider another component that is known as a Coriolis component, right? The Coriolis component is present where sliding contact occurs between two rotating links. So that is the case of Coriolis component of acceleration. The type of acceleration that is encountered is in the relative acceleration of 2 points when the following 3 conditions are to be met. That means you have to consider these 3 conditions, then and if these 3 conditions are satisfying, then that means the Coriolis component has to be considered for that particular during the acceleration analysis of that particular mechanism, right? So here the condition is that the first condition is that the 2 points are coinciding. That means here the point B on link 2 as well as the point B on link 4 is actually coinciding. Okay, so that means the first condition is being met in this particular case. The point on one link traces a path on the other link. That means here the point B on the link 2 is actually tracing a path along the link 4. So that is another case. The link that contains a path rotates. That means if you consider the point B on link 4, then you can see that point B is actually rotating. Now, if I consider point B on link on the slider, you can see that it is sliding. It is having a linear motion. And now if point B is on link 2, then you can say again point B is rotating. That means this point B, which is a common point for all the three links, is actually having a complex motion. It is having a sliding as well as a rotary motion. So in such cases, we have to go for considering the coriolis component of acceleration. Now, what to be done is, if I consider the velocity of point B, uh, which is lying on link 2, that means we are just considering that the point B is associated with link 2, link 3, and link 4. That means it can be referred as B2, B3, and B4. Okay. So in such cases, we are just, in that particular case, I'm considering the uh, point B which is lying on link 2. Now in such cases, if point B is lying on link 2, then the acceleration of point B with respect to the absolute acceleration of point B which is lying on link 2 can be written like this. That is the acceleration of uh, B which is lying on link 4, right? Now we are imagining that this point B is lying on link 4. That's why the acceleration of B with respect to the link 4, and you have to consider the relative motion between the point B on link 2 as well as link 4. Okay, that means we have a point B on link 2 as well as point B on link 4. Both is having a relative motion. So definitely the absolute acceleration of the point B which is lying on link 2 will be equal to the absolute acceleration of point B lying on link 4 plus the relative acceleration of point B lying on link 2 with respect to the point B lying on link 4. So that's what is being written here, right? So here, uh, for our consideration, we are just taking this particular relative component only because this acceleration is absolute acceleration and this one is also an absolute acceleration. This can be called as the acceleration of B with respect to the fixed point of rotation of link 4. That means the fixed point of rotation of link 4 is point C. So AB4 can be considered as taken with respect to point C. That means we're just considering the point B lying on link 4. So the absolute acceleration of B4 means it is the acceleration of B4 with respect to point C. Okay, so that is the absolute acceleration, right? Now this acceleration AB2 bar AB4, AB2 bar B4 is actually the relative acceleration of B2 with respect to B4, right? Now for that particular acceleration, we can segregate as like this. Again, we can see that all the three conditions are being met. That's why we are taking that particular quantity here. Now, the relative acceleration of B2 with respect to B4 can be written as, now if I draw it and show it, you'll be able to understand it quite clearly. Now, here I have one particular link, and I'll show a point here. And another point here. And call this as B4. B4, and this one is B2. Okay. Okay. Now, what is to be understood is that this is a fixed point. The bottommost point of the link is a fixed point. That is a fixed point. Now, initially imagine that this B2 and B4 are coinciding. That is, B2 is lying on over B4, right? Initially, you can imagine like that. After a fraction of a second, you can see B2 has been moved up a little bit, and B4 is, I'd say, at its initial position, because B2 is lying on link 4. This is actually link 4. You can consider this as link 4. This is link 4. Okay. Now, that's what I'm trying to say is that this B2 and B4 initially was at the same point, and after some time, after a fraction of a second, you can see B2 has been displaced from B4 to a certain distance. Now, in doing so, initially, what we normally does in the as in the previous cases, we try to identify what is the acceleration of B4 with respect to B2. If B2 and B4 are at the same point, that means we'll be considering only the centripetal acceleration and then the tangential acceleration at that point. So these are the two components we normally consider. Now, since B2 is being moving in the next instant, normally we are actually not trying to analyze that particular motion. In the normal case, we don't try to analyze that particular motion. And because of that, because of the defect in the acceleration analysis, a lot of problems has happened in the design of the mechanisms, and which actually collapsed during their operation. So later on, they identified that such a component arises because of the relative motion between the coinciding points. Thus, they reached up to that particular conclusion that such a component exists, and that's what we are trying to identify how that component is acting. Okay. Now, this is how it happens. That means initially B2 and B4 were at the same point. So in the normal way, we do the once you draw the acceleration analysis, we do that. This B2 and B4 will be having a centripetal component which is directed to the center of rotation, and another one a tangential component which is perpendicular to the link, right? So these are the only two components. Now, if I consider the relative motion between B2 and B4, uh, there also these two components has to come in. There also these two components has to come in. That means there are also the centripetal component and the tangential component has to come in, because there has been a relative motion between those 2 points. So that means the component that has come in is actually the normal acceleration and the tangential acceleration. That's what is being written here. The normal acceleration of B2 with respect to B4 and the tangential acceleration of B2 with respect to B4, and that's what you normally does. Okay. And there is another component which is equal to the coriolis component of acceleration. Okay. So that's what is being written here. Now, this is the component which we need to analyze. These two components we already know, because that is the normal component and the tangential component, right? Now, this component of coriolis component is indicated as the magnitude is shown here. It is twice the relative velocity of B2 with respect to B4 into the angular velocity of the link on which B2 is being moving, right? So that means the angular velocity of link 4. Here it is link 4, so you have taken the angular velocity of link 4, right? So that is twice the relative velocity of B2 with respect to B4, and this relative velocity can be obtained from the velocity polygon, right? Twice the relative velocity of B2 with respect to B4 into the angular velocity of the link on which that particular component is sliding, right? So this is the magnitude of the Coriolis component. Now, if I consider the Coriolis component, the magnitude is already obtained, but the direction has to be understood. The direction of the component has definite significance, because once you go for the graphical analysis, we have to understand what is the direction of the Coriolis component. Now, for that, you have to just identify what is the direction of rotation of this link. First, you have to identify what is the direction of rotation of this link. That means the direction of omega has to be identified. That means omega 4 needs to be identified. The direction of omega 4 needs to be identified. And also, what is the sliding direction of the, what is the direction of VB2 with respect to B4? That also needs to be identified. So here in this particular case, I can see that this velocity of B with respect to B4 is moving in the upward direction, is it not? This is the direction of the sliding velocity of B2 with respect to B4. This is the direction of BB2 with respect to B4. So I can write that there. So this is the direction of velocity of uh, B2 with respect to B4. Okay, that is what is being seen there. That is the direction which is being shown by this vector. Now, since I know what is the direction of vector, now for the time being, I'm just considering the direction of angular velocity omega 4 is in the clockwise direction, right? Now, suppose omega 4 is in the clockwise direction, then the direction of the Coriolis component will be like this. The direction of Coriolis component will be like this. Now, I can call it as V C is B2 respect to B4. The suffix. Okay, so this is what you see as the direction of the Coriolis component. Because what you try to do is you identify the direction of the sliding velocity and rotate that vector in the direction of angular acceleration of that particular link 4. Here it is link 4, that's why I'm saying it as link 4. So the sliding velocity direction is being rotated by an angle of 90 degree in the direction of omega 4, so that you will be getting what is the direction of the Coriolis component. So that's what is being done here. So this is the direction of the Coriolis component, and the magnitude is being given here. So definitely you can find out what is a vector. Now, based on that particular vector, you'll be drawing the acceleration polygon. Okay. Uh, so whenever you come across such a sliding condition, you will be utilizing this particular technique in order to identify what is a Coriolis component, so that the acceleration analysis will be complete. Okay. So for today, I am stopping here. You just go through this tutorial, this particular video, and understand it clearly, so that in the next session, we'll be discussing example using this Coriolis component, and we'll do the acceleration analysis for that one. Okay, thank you then.